We finished the sampling distribution topic, and now we want to move our attention to confidence intervals. Sampling distributions are a great theoretical tool, but really we don't do a whole lot with them, or we can't do a whole lot with them. If you think about the sampling distributions, we're talking about repeated sampling. We're going to sample over and over and over again from a population. Well, that's just something we don't want to do, but we need that idea in order to get some information from a single sample, and that's what we want to do here in confidence intervals. We want to try to determine what kind of information can we get from a single sample. And so here we begin with a definition we've seen before, the definition of a point estimate. It's the sample statistic that provides the best guess at the value of a population parameter. Two terms here, statistic and parameter, we've seen before. Remember, the parameter is a numerical measure that describes a population. So what we're going to be interested in this particular lecture is a population mean. So population mean mu. We don't know those values. We don't know parameters. But we do know statistics. We take samples and we have values like the sample mean, the sample median, the sample mode. And we're hoping that we can use those sample statistics to get some kind of estimate at the value of a parameter. Now a point estimate is just a single point. When we get a sample mean, it's just a single value that estimates a population mean. It doesn't have any kind of reliability attached to it, but it is our guess. It's our best guess. And so what we want to do here in the beginning of the confidence interval section is to talk about how do we estimate a population mean using a large sample. And our definition of large sample, as we saw, was greater than or equal to, the number that we're going to use is 30. And that comes from our central limit theorem, which we're going to have to use with our large sample. We're going to need that as part of what we do here in just a second. Now the reason we start with the large sample case is because we know some stuff. We know from our sampling distribution some work that's going to be necessary here that'll help us to estimate mu. And so here's how we're going to do it. And the way that I'm going to present confidence intervals to you, I want you to understand, I want you to see that confidence intervals, it's kind of a technique or a tool that we have in statistics. It's a first real inferential tool that you guys have been introduced to. And when I say inferential, taking sample information to make statements about populations. This confidence interval tool we're going to use over and over and over again. In an introductory stat class, you're going to see several applications of confidence intervals. As you move further along in statistics, you see more and more applications of confidence intervals. So what I want to try to do is present this confidence interval idea to you as an idea, as a tool with several applications. So while I'm going to specifically be working in the large sample case for a population mean, I want to think bigger than that. I want to think, how does this idea, how will it apply to small samples? How will it apply when we look at population proportions? How does it apply when we move to regression analysis? There's a lot of places you're going to be using these confidence intervals. And all of them get their start here. We need a parameter that we're estimating, and we need some way of estimating it. Okay, so we start with mu, and we're going to estimate it. We know that x bar is our best estimate. It's better than the median, definitely better than the sample mode. But we also know, because we looked at our sampling distribution work, that from one sample to the next, these guys vary. They move around. If I take a sample of students and calculate their average age, from one sample to the next, that number is going to move because the people in my sample, their individual ages or their x's, will vary. And so we need to understand that variation. And again, this idea, we're going to talk about it, we're going to come back and talk about it with small samples. We're going to come back and talk about it with proportions. We need to understand the sampling distribution of the point estimate. Now this is the one we know about. We just got done looking at this. We know that when we're working with the sampling distribution of x bar, there are three pieces that are always true. First, the mean of the sampling distribution of x bar is mu. We said back in the sampling distribution section, we called this an unbiased estimate. We know that the standard deviation of the sampling distribution of x bar is not sigma, it's sigma divided by the square root of n. And these two things are always true, and by themselves we can't do a whole lot with them until we get the shape. And that's what the large sample gives us. And now you see I put central limit theorem in parentheses here. That theorem gives us that the shape of the sampling distribution is approximately normal. You know how to work with this. We've worked with normal distributions before. We've seen z-scores. Well, the z-score that's going to be appropriate now is the x bar version. And I can write this a couple ways. I'm going to write it this way. I'll write it this way on this page. We'll see it another way in just a second. Actually, you know what? I'll write it both ways. It's x bar minus mu divided by sigma over the squared area. Now another way of writing this, and you're going to see this on the next couple pages in notes, or at least the next page. We can subtract off the mean of the x bars, which is mu, and then in the denominator here I'm just going to write sigma of the x bars, which is sigma over the square root of n. It's just going to be easier to see it this way on the next page. But we're going to be able to work with normal distribution while we're working with the sampling distribution of x bar. All right, now this is stuff we know. When we go to a small sample, when we change from a large to a small sample, when this number gets less than 30 over here, these two are still going to work. This is the one that we have problems with. That's the one that's going to change, and so we're no longer going to be able to work with normal distributions. But we'll get to that. That's another story, another lecture, another video in your not too distant future. So how do we work with this? Well, let's turn the page. Now I took the normal distribution that we were looking at before and kind of blew it up. It got a little fuzzy on us here, but just go with me. And what I've done is this is the sampling distribution of x bar, so it's going to be a normal distribution. Let's call it a z. It's going to be, actually let's just call it a normal distribution. Let's label this. Let me label this differently. Let's just say this is the sampling distribution of x bars. We'll get to z's in a minute, but we're not there quite yet. It's centered at mu, and I've come out here almost 2 standard deviations. Now, the values that I'm going to end up at are mu plus 1.96 standard deviations, and at sigma that should be x bar. I don't know how that's going to show up in your notes, but there's a line over there. And this is mu minus 1.96 sigma sub x bar. I'm going 1.96 standard deviations from the mean. Why not 2? Because I know some things. I know some things that you'll be able to see in just a minute that make the 1.96 number a little bit nicer. Here's where I want to start. And I guess I should give you a warning. This page is ugly. You guys are looking at your notes in front of you. You know it's ugly. But let's kind of go through it. See if you can follow. See if you can make sense to you. What I want to figure out is the probability, not that x bar falls in between here, but the whole thing. I want all this probability. The probability between mu minus 1.96 standard deviations and mu plus 1.96 standard deviations of x bar. What's the probability x bar falls between these two values? And when you look at this, a lot of times students look at this and are like, I have no earthly idea. I don't even know what you're asking there. Well, if you think about it, because we're dealing with a large sample, this is a normal problem. How do we solve normals? We change them to standard normals. And so we're going to use the z-score transformation thing that we've been doing a whole lot of. Over the last couple of weeks, you guys should have been doing a whole lot of problems where you're changing normals into standard normals. And because we're asking about x bar, this is going to be the x bar version of the z-score. All right. So what happened there? Well, I'm doing the transformation on the x bar. I'm subtracting the mean of the x bars. I'm dividing by the standard deviations. The goal of this was to get a standard normal value, a z value right here. And I did that by subtracting the mean of the x bars and dividing by the standard deviation of the x bars. On either side, I have to do the same thing. I have to subtract mu sub x bar, and that's what I'm doing over here. I'm taking the point of interest, mu minus 1.96 standard deviations. I'm subtracting the mean of the x bars. I'm dividing by the standard deviation of the x bars. And I'm doing it on this side as well. I'm taking mu plus 1.96 standard deviation, subtracting the mean, dividing by the standard deviation. And this parenthesis here is a bad one. That shouldn't be there. Don't know how that snuck in there. Okay? And so you're looking at this thinking, holy cow, this is a mess. But is it? Let's take a look. Take a look at the numerator here. You have mu minus that. Forget about that for a second. What did we say the mean of the x bars is? Go back on the last page. The mean of the sampling distribution of x bar is mu. This value and this value cancel. They're exactly the same value. You get a mu minus a mu, so they just cancel. And then you're left with minus 1.96 standard deviations of x bar over the standard deviation of x bar. These things will cancel as well. And so while this was extremely ugly on both sides here, we get a lot of cancellation, and we end up there. The middle thing is just a z, and these weird numbers that I started with, well, I knew that's what we'd end up with down below. I knew that the mean and the standard deviation would just cancel out, and I know that, and you guys are looking at this thinking, oh my gosh, what do we need here? Just trying to prove a point. There's a couple steps we got to get through here. And the first is that when we look at these values here, 1.96 standard deviations away from the mean, well, you can find this value. You can look this up in the z-table. Go get a z-table. And if you don't have one, pause the video, get a z-table, and look up the z-score 1.96. I bet you see the value, 0.4750, but prove it to yourself. That's what I found. But that's referring to this probability in here, the probability between 0 and 1.96. When you take this to a standard normal distribution, the mean becomes 0, this value becomes 1.96. The probability in here is 0.4750. The probability in here on this side is also 0.4750. So we're saying the probability between mu minus 1.96 standard deviations and mu plus 1.96 standard deviations is 0.95. In repeated sampling, a phrase we're trying to get away from. That's kind of the point of this section. We want to get away from it. We're not going to be able to completely get away from it, but we're trying. If I was to sample over and over and over again, what I know is that 95% of the X-bar values would fall between these 2 points. 95% of them. Occasionally I'd get one that falls outside on one side or the other, but the vast majority of them, 95% of the X-bar values will fall between those 2 points. And that's step one. It's all you need to recognize. This is ugly. Look at this page of notes. This is horrible. You start with a normal. It's an X-bar normal. We changed it to a standard normal. We get our standard normal numbers. We look them up in the table. And if you step back and think of it from that perspective, we've been doing that for a while. Now this one's a little uglier because there's a lot of symbols instead of just numbers, but it's basically the same process. Start with a normal, change it to a standard normal, look it up in the table. All right, so hopefully that makes a little bit of sense. I know it's a little ugly with all the symbols, but hopefully you can see where I got that from, and you're shaking your head. You're thinking, yeah, I see that. Okay, I see where the 95%. If I change this number here, this 1.96 number, if instead of plus and minus 1.96, I made it, let's say I made it plus or minus 2.3. So maybe if I moved it out this way, what do you think is going to happen to that probability? Isn't it going to go up? If I move these lines further out in the tail, isn't the probability in between going to be a bigger number? Likewise, if I take those numbers and make them smaller, maybe I make them 1.75, and we'll run into that number probably a little later. But let's say I make them 1.75. I pinch them in a little bit. Isn't the probability inside those two values going to be smaller now? Isn't this reliability level, this confidence level, this probability right now, isn't it tied to the 1.96 number? Just something to notice. We'll come back to that thought, but that's just something to notice right now. And so that's a good starting point. In repeated sampling, 95% of the X-bar values fall between those two values. All right, this next picture. This is the biggie. This is your confidence interval picture. Put an asterisk on this one. This is hopefully going to help you understand what confidence intervals are, how they work, how we interpret them. We get a lot from this picture. And you can see what I'm starting with is the same distribution, right? And I'll put X bar here. We'll draw in mu here in the middle. All right, it's going to take some imagination, and hopefully with the cursor I'll be able to draw this pretty well. Remember, this is the sampling distribution of X bar. If you sampled over and over and over again, this is how the X bars would pile up. We've talked about that numerous times now. So here's what I want you to think. Let's think about a population. Let's think about the population I'm going to talk about a little later is GPAs of students. GPAs of students. Let's think about a private college. Let's say it's a smaller school. Let's say there's like 3,000 people there, 3,000 students. And I'm interested in learning about the average GPA of all the students at this school. Now, I don't want to talk to all of them. That's a lot of people to talk to. So I'm going to take a sample. And so let's say we take a sample of 30 students, nice large sample, just barely got there, right, 30, and calculate a value of X bar. So I go into the school, I randomly sample 30 students, and I calculate a value of X bar. Okay, now, that X bar value is going to fall somewhere in this distribution, right? I'm not sure where. It's going to be one of the values in the distribution. And the idea is if I sample 30 other students, I put those 30 back. They could be sampled again. Some of them might be, some of them won't be. But I take another sample, get a different value of x bar, that x bar value is going to move. Because the GPAs that I get from one sample to the next, the students that I get, and hence their corresponding GPAs, are going to vary a little bit. And so the x bar values are going to pile up. And that's what we talked about. That's what we call the sampling distribution of the sample mean. And we know, because of the central limit theorem, that they're going to be approximately normal. We know it's centered at mu. We know the standard deviation is sigma over the square root of n, which goes right in the sequence of x bar. Okay, we got all that. We know that. But here's the point. If we take a sample and we get a value of x bar, because we don't know the value of mu, when I look at the x bar value, if I get a sample GPA, a sample mean GPA of, say, 3.2, I don't know where that falls in this distribution. I'm not sure, is it above the mean? Is it below the mean? We might have a guess, but do you really know? Or let's take an example where maybe you've never seen the data before. You have no idea. And you get a value to sample mean, but because you're not familiar with the data, you have no idea if it's above or below the mean. That's the idea here. The values of x bar are going to vary. And so if we take a sample, and I'm just going to put it in, I'm going to draw a little dot. Hopefully that shows through. I'm going to make it a little bit bigger just to make sure. Let's say we get a sample mean and it falls here. Now, of course, we don't know that it falls there because we don't know where it is relative to mu because we don't know mu. But that's the value of the sample mean that maybe we got in a sample that we selected. All right, now if you look up top, suppose we repeatedly sample and construct. I'm not saying just look at x bar, I'm saying do this. Take x bar plus or minus 1.96 sigma sub x bar. And again, I'm going to make that bar a little bit larger because on my screen these bars are looking a little weak. I'm going to put them in a little bit better. I'm saying add and subtract 1.96 standard deviations of x bar to and from the mean. A lot of times, again, students are like, what the heck does that even mean? Well, if I'm standing here at mu and I decide to walk over here, how far did I travel? Didn't I go 1.96 standard deviations? Or if I'm at mu here and I decide to walk over here, if I've drawn my picture correctly, and it's looking pretty good, these lines should be equally spaced around mu. What I'm saying is take a look at this distance right here. That's 1.96 standard deviations. It should be the same distance as this guy right here. Oops, I should stop that right here. Between these two lines and between these two lines is 1.96 standard deviations. What I'm suggesting we do here is let's take that distance and add it to the x bar value. And I'm going to put a parenthesis, a closed parenthesis. And let's take that distance and subtract it from the x bar value. Now the point estimate's right here in the middle. That's our x bar value. And then we're adding and we're subtracting 1.96 standard deviations of x bar. The point estimate is just a single value. That's the value right here in the center. Interval estimation or confidence intervals, you start with that center point and then you go around it. I'm sitting here with my hands right now. You can't see this obviously because we're on video. But I'm sitting here and I got my hands together at the point and then they separate to the endpoints, and the left and the right hand are kind of going apart from one another, and I'm thinking about them going to 1.96 standard deviations on either side of the mean, and we get these endpoints. Now, at some point, we're going to find these endpoints on a printout. They're going to be called the lower endpoint and the upper endpoint. But the thing I want you to notice about this interval, notice what value is inside of those endpoints. It's the value of mu. This interval captures the mean or encloses the mean. It contains the mean. I'm going to call this, here's a real technical term for it, I'm going to call it a good one. This is a good interval, and that good is spelled G-O-O-D. Okay? Now, the theory of confidence intervals doesn't say stop there. The theory says do it again. Take another sample. Okay, so the sample that we had, let's throw them back into the mix, into the population. We're going to go and take another sample. We're going to get another large sample. We're going to get another value of x bar, and the thing that you got to recognize is because we're dealing with sampling distributions, the value of x bar we get this the next time is going to change. Here's where we got our first x bar. Maybe the next value of x bar falls, and I'm going to draw it a little bit higher because I'm going to draw some intervals, and I don't want them to overlap. Maybe the value of x bar fell right there, the second sample. Notice how close it is to mu. Now, of course, we don't know this because we don't know the value of mu. We're just looking at our sample mean, and we're thinking, there's our sample mean. Much like when we looked at this sample mean over here, we said, well, there it is. That's our sample mean. We get different values of x bar from one sample to the next. But again, I'm not just going to look at the value of x bar. I'm going to add. Wish I could draw straighter lines for you guys. And subtract. .96 standard deviations, and I get a second interval. And you notice, or I hope you notice, it's a good one. It's contained mu. And we're going to do it again, and again, and again, and again. Now, I'm going to draw a couple more intervals here and talk about what would happen. Let's say the value of our sample mean fell way out here. And if you look at how far it fell from mu, man, that's not even really all that close, is it? It's pretty far away. Yet again, when I do 1.96 standard deviations, now when I'm going this direction, I'm getting really far away from mean. But when I do the 1.96 standard deviations here, just barely, but it captures mu. I'm 3 for 3. Keep going. Keep doing it over and over and over again. In fact, the theory says do this forever. Obviously, we don't want to live in theory world. But think about it. Think about what would happen if the value of x bar were right here. Would you get a good interval? Yeah, you would. How about if the value of x bar were right here? Yeah. How about here? How about here? How about here? How about here? In fact, really what I want you to be thinking is, where would a value of x bar have to be located in order for the interval to be bad, to not contain mu? Now, hopefully you're following along. Hopefully this is making sense. If the value of x bar, say, falls out here on the other side of this line, or on the other side of this line over here, but when I do my 1.96 thing, it's going to come up a little short. That's a bad interval. And so do this over and over and over and over again. Here's what you need to see. In repeated sampling, 95% of the intervals created would contain mu. Why 95%? Every time the x bar value falls between the 1.96 and the negative 1.96, we're going to get an interval that contains mu. That's what you should see from this picture. Anytime the value of x bar falls outside, we get a bad interval. Well, we said on the preceding page that 95% of the x bar values will fall between those 2 points. So in repeated sampling, 95% of the x bar values will lead to good intervals. The way we're going to say it is this way. 95% of the intervals created would contain mu. This is the theoretical interpretation of reliability right there. We'll come back to it. We'll see it again. That works for confidence intervals for mu. That's going to also work for confidence intervals for proportions. It works for large samples here today. It's going to work for small samples when we come back. This is the confidence interval idea. This is your confidence interval picture. Think about these intervals moving around. And typically what I'll do when I talk to students is I talk about how from one interval to the next, and again, I'm sitting here with my hands in front of me. I got them probably about maybe 1.5 feet apart. I kind of cup in my hands so that they look like my hands are actually imitating the parentheses. They're kind of cupped, and they look like parentheses. And really what my hands are doing are showing the endpoints of an interval. I'm looking at one of these intervals, and now when I take a different sample, all I do with my hands is I kind of shift it to the side, because when I move from this interval right here to this interval right there, all that's really happening is that the center of the interval shifting. They're dancing, they're moving, and I refer to these intervals as the dancing intervals. The intervals dance around the value of mu. Most of them capture mu, some of them don't. That's a theory of confidence intervals right there. That's how confidence intervals work. The odds are squarely in our favor. We're going to have a chance to increase that probability if we want. We get to play around with that number a little bit. If 95% is not high enough for you, well, we can do 99%. Sometimes 90% is what we use. But that's the theory. Now, what we do is we call the one interval we actually construct, this guy right here, we're going to only do it really once, but we're going to call that interval a 95% confidence interval for mu. Now, I don't know if I have a good one or a bad one, but I know the odds are really in my favor. The probabilities are really squarely behind me. 95% of the intervals would be good, and here's the one I'm looking at. And we're going to be looking at some numbers. We're going to have some endpoints. We're going to be able to make some really cool interpretations. And so we take this repeated sampling idea, the theory, and we turn it around and express it as a confidence statement about our one interval. Now, let's get some terminology out of the way. 95% is referred to as a confidence level, and you'll hear that term quite a bit. Some people use, a lot of books use confidence coefficient. As you're working with the table, a lot of times you have to go through the decimal expression, 0.95, but that's your confidence coefficient. But then there's the 0.05. If you're 95% confident, you can also think of this as 5%. That's your error rate. That's how much you're missing by, or that's how many, the percentage of the intervals that are going to be bad. We give it a symbol, and this is the Greek symbol alpha. It looks like a fish. In fact, it's one of the few symbols where if you call it the fish, I'll be okay with. A lot of times students call it moo. Not right, not good. They botch sigma. But here, if you want to refer to this as a fish or alpha, that's fine. I'm going to actually use a fish a little bit later when we talk about test hypothesis. I'll use that terminology. I'll use it to our advantage. We'll talk about fishes and ponds, and we'll get to that. But that's 0.05. That's the error rate. That's our confidence interval theory. In repeated sampling, 95% of the intervals created would contain the population mean. Well, here's our formula. Okay, and I've given you really two different forms here. Now, in the last, what do we have? We had this. This 1.96, and a lot of times I write the sigma subscripted with the x bar. Well, that's become this guy over here. I'm taking the 1.96 out. The 1.96 is tied to our z value. Okay, 95% reliability gives us a z value of 1.96. Typically, the expression you're going to see, and the font I used is in grade here. This is the expression, z subscripted with alpha, that error rate, divided by 2. And I'll talk about this and explain this in just a second. So 95% confidence leads you to a 1.96 value here. And then the sigma sub x bar, I'm just expressing it as sigma divided by the square root n, just another way of saying it. This is typically thought of as the formula, excuse me, the large sample formula for a confidence interval for mu. Over here, what you see I've done is we typically don't know the value of sigma, so most of the time we just plug in the value of the sample standard deviation s, and that's how we're going to do our calculations. Now, most calculations are going to be done with a software package. We're not going to have to do the math. I am not interested in a lot of math. What you're responsible for is being able to find the z value. I want you, and this is a skill you guys should already have, but I want you to be able to go to a z table and tell me that if I'm 95% confident, the z value is 1.96. And I'm also going to ask that you be able to interpret these confidence intervals. And we'll talk about that, because interpretation is going to be a key. At some point, you're going to have to worry about some assumptions. We don't really have to worry about that right now. We need to be randomly sampling. That's about the only thing we do need. But we'll get some assumptions a little bit later that you will be responsible for. All right, so let's take a look at an example where we're going to find a z value. And I'm going to change. There's three really common levels for confidence levels. 90%, 95, 99. 95% gets you to the 1.96 number. What I want to do is walk you through this notation, this terminology. It's not great, I'll be honest with you. When we work with small samples, the notation is going to be a little bit better. But for right now, this z notation, the z alpha over 2 thing, is not all that great. But let's find a z value for a 90% confidence level, or a confidence interval. If you have a 90% confidence level, what's your alpha? Well, that's the opposite of that. If 95% goes to 0.05, 90% goes to 0.10. So half of your alpha is 0.05. Now, what we want to do is take a look at a z distribution. Okay, and we've looked at this, once or twice or a couple hundred times probably by now. But that's how we start our z distributions. This alpha over 2 notation says put alpha over 2 in the tail. If you think about it, what did we have before? We had 95% was in here. What's left over? Alpha. That's outside. So we're going to put alpha over 2. That's a lousy alpha. That's better. We're going to put alpha over 2 in both these tails. And so in this case, we're going to put 0.05 out there. And then this value here is referred to as z subscripted with alpha over 2, and the one over here is a negative z subscripted with alpha over 2. Now, in the past, you've had to worry about, is it positive, is it negative, which value am I going to use? Well, our formula is going to use plus or minus. It's going to take x bar plus or minus the z value, so it really doesn't matter. You just need the number. But in our case, we're going to put 0.05 in both tails. All right, now, why do I say this notation is pretty bad? All right, well, the notation is z subscripted with alpha over 2. And here's what we got. We got a picture with a 0.05 in both the tails. And if you look at the screen right now, if you just look at it right now, I got 90% written here. Okay, or that could be 0.9. I have 0.1, I have 0.05, and here's my question to you. How do you find this z value? Use your z table. How do you look that up? What number do you look up in the z table to find this number? And I'm having way too much fun with this arrow over here, sorry. You don't look up the 0.05 because our table doesn't work with tail probabilities. You don't look up the 0.10. You don't look up the 0.90. Remember, it's our z table. We look up this inside probability, 0.4500. And again, if you don't have a z table, it might be worth your while to pause the video and go grab one real quick. Hopefully that pause was long enough for you. If you don't have one, hopefully you got one. When you look up the the probability 0.4500 in the table, it falls right in between two numbers. You see the 0.4495, you see a 0.4505. Happens at the z value 1.64, somewhere between 1.64 and 1.65. The value that we're going to use is 1.645. That's what we're going to take from the table. And we're going to use that in our formula in place of the 1.96. And so if you want a 90% confidence interval for mu, we're going to plug in a 1.645. If I change this to 99%, well, that number is going to change, and that number is going to change, and that number is going to change. If I change it to 93%, we'll take a look at another example in just a second. But I want you to be able to find the z values in the table. Again, it's a skill you already have. We've been looking at the z table now for a while. So it's nothing new. It's just using it in a new place. So that's how you find the z value. Now, let's take a look at an example. I am interested in estimating the average GPA of all students at a private college. The example I talked about earlier. Let's say there's several thousand students at this college. I randomly sample 235 of their students and find the sample mean. Okay, now this is a number. What symbol would you give to that? The average GPA of all students, that's what we want to learn about. That's mu. But what's this guy here? Isn't that an x bar? That's a sample mean. And a standard deviation here, that's an s. Use this data to calculate a 92%. That's an interesting choice. Confidence interval for the population mean. Really, I just wanted to choose another value to go through the process, go through the thought process of how we come up with those z values. We want a confidence interval. Now, you see a sample of 235, large or small. Well, hopefully you're saying that number's 30 or more. It's a lot bigger than 30. That's a large sample. We're going to use our large sample confidence interval. Now you can see I got a bunch of numbers already underlined. 235, that's going to go here. 0.4932, that goes here. 3.2, that goes there. Really, the only thing we need to find to do the math here is the z value. And so we go through our process. Alpha, in this case, is 0.08. 92%, 0.08, 8% is the opposite. 92% confident, 8% error rate. Alpha over 2 is 0.04. We need a normal table. Here we go again. We're going to put 0.04, put alpha over 2 in the tail. That's a lousy 0.04, but there you go. Over here, we're going to put let's make this 0.04. Put that in this tail here. So what's this probability? 0.4600. Look that one up in the normal table. I think that's pretty close. If I remember correctly, that falls really close to 1.75. That's the value right here. And this is going to be negative 1.75. Again, in the past, it's like, oh, which one do I use? It doesn't matter. Look what we're doing. We're adding and subtracting. We're going to do both. And so you plug them both in, or either in. It doesn't really matter. Just put in a 1.75. So now you should see that these calculations aren't real challenging. We put the 3.2 in for x bar. We put the 0.4932 in for s. Excuse me. We put 235 in for the n. It's a math game. Now, I'm not real interested in you doing this math. Again, we're going to look at, and I'll show you how the computer's going to do these numbers for us, how we get these values. There is a skill here. I want you to be able to find z values for me. You can see I did the math for you. 3.2 plus or minus 0.0056. A lot of times homework answers in textbooks leave their answers this way. Think about what's going on. We're getting an x bar, 3.2, plus or minus a 0.0056. We're going to get an upper endpoint. That's what you see in this next row here. We get an upper endpoint and a lower endpoint. That's your confidence interval. Is it a good one or a bad one? Well, that's a great question. That's a really good question. And that's where we go next. And so our confidence interval goes from 3.144 to 3.256. So your job, remember what I said, or you're responsible for, I want you to be able to find the z-values, and I want you to be able to interpret the confidence intervals. So let's talk about interpreting confidence intervals. And again, let's see, what was that confidence interval? 3.144 to 3.256. Just going to write it up here. That's the confidence interval from the preceding page. That's what our math got us to. Now, how do we interpret that? Well, I'm going to ask you to work with 3 interpretations. The first one, the one you see in front of you here, is called the practical. What are we trying to do? Early part of the problem, what did I ask? Estimate the average GPA of all students at this private college. Well, here are practical interpretations. And again, let's take a big picture. I talked about how those dancing intervals, again, my hands are swaying back and forth as the intervals are dancing, how that works for the large sample mean, but that's the theory of all confidence intervals. That works for small samples. It works for different parameters. What we're going to do is take that and express that as a reliability level in R1. So when I talk about the interpretation, this is how we start practical interpretations. We start with our confidence level. We are 92% confident that. In this problem, 92%. This number may change. We already talked about a 95%, 90%, 99%. Those are some numbers I've talked about today. Start with your reliability. We are 92% confident that. And then the second part, which I'm going to come down here, this whole part from here to here, that's the second part. First part's your reliability. The second part is your parameter. In a symbol, if I wanted to summarize in a symbol, I'd say mu. But typically people don't talk in symbols. People use words, and that's what I'm going to ask you to do. I'm going to ask you to interpret things with words. The mean GPA of all students at this private college. It's important. All. Not just the, 235 students or whatever it was on that last page. It's all. The mean of all. We're using our x bar from the subset, from the sample, to make a statement about all, the mean of all. So the first part's the reliability, the second part is your parameter, and then lastly are your numbers. We are 92% confident the mean GPA of all students at this private college fall between 3.144 and 3.256. I don't know exactly where it is, but this is where I believe it is, and I'm 92% confident in that. That's the practical interpretation. We're trying to estimate mu. The practical interpretation says, here's what we think, and here's our reliability. If you leave the reliability out, you're selling yourself way short. Usually at this point in time, I say, listen, you guys earned it at this point. You survived probability. You've looked at Chebyshev, the empirical rule. You survived the binomial distribution. You learned the normal curve. You've done a lot of stuff. You've earned this reliability at this point in the semester. Use it. Don't say we think or we hope. Don't say you're 100% sure, because that's just not true. We're 92% confident in this problem that the mean GPA of all students at this private college falls between these two numbers. The second interpretation says, all right, I hear what you're saying here. You say you're 92% confident, but what do you mean by that? And this is where I want you to go back. Remember that picture we looked at just a little while ago? We put the asterisk on it. If you look at that picture, it says in repeated sampling, 95% of the intervals created would contain the true population mean. Here we're going to change it. 92%. If you want to use mu here instead of population mean, I'm usually okay with that. I want you to spell out the words of the problem somewhere, and usually it's in the practical interpretation. In repeated sampling, 92% of the intervals created would contain mu. Constructed would contain mu. It's perfect. This theory is talking about the dancing intervals. 92% of those intervals are sliding left and right. They're moving, and again, my hands are sliding left and right in front of me. 92% of them would contain the population mean. So that's explaining, the theoretical is explaining the reliability, the 92%, the confidence level. And then the third type of interpretation, a lot of people stop there, but I'm going to go one more. I'm going to ask you some questions. I'm going to say, take a look at our interval, and again, it's at the top of the screen here. Maybe someone claims that the mean is 3. What do you think? Is the mean 3 or is it bigger than 3? How would you respond? Look at this interval. It goes from 3.144 to 3.256. 3.144 to 3.256. All those numbers are bigger than 3. So a lot of times students want to say, yeah, I think it is. You can do better than that. Sometimes students say, yes, it definitely is. You can't do that good. We are 92% confident the mean is bigger than 3. At our 92% confidence level, every single one of the values, and sometimes we talk about these confidence intervals as being a set of believable values for mu. I could be persuaded to believe that mu falls anywhere in there. And all of those values are bigger than the number I asked you about, 3.00. And so I'm going to say we are 92% confident that mu is greater than 3. Now sometimes students say, well, can't we do better than that? Can't we be more than 92% confident? Because it's not like 3 falls right here. There's a little bit of space between this endpoint and where maybe 3 falls over here. Can't we be more confident? And what I like to say is sometimes students want to get confident greedy. Can I increase the confidence level and still make this statement? It's a great question. It's one we're going to look at. But I'm going to hold that thought for right now. All I want you to do right here is say, look, 3 falls outside the interval. If I asked you, is mu equal to 3.5? You should tell me you're 92% confident mu is less than 3.5. We're 92% confident that mu is less than 3.3. We're 92% confident mu is greater than 3.1. Anytime I ask you about a value that falls outside the interval, you're going to be able to make a strong statement like this. But what if I ask you this? Is mu greater than 3.15? And if you look at this, I'm going to put the interval kind of on a number line here. Okay, here's the lower endpoint, 3.144. Here's 3.256. Where's 3.15? It doesn't fall like right there, just barely inside that lower endpoint. Just, If I asked you about 3.14, you would say we are 92% confident that mu is greater than 3.14. But here's how we're going to answer the question. Is mu greater than 3.15? Maybe. At the 92% confidence level, the mean might be bigger than 3.15. And you're saying, but all these values are bigger. But there are some that are less. There's a possibility. That's the best we can do. And that's where students are like, I really wish we could do better than that. Yeah, me too. I really do. But we can't. At the 92% confidence level, the mean might be bigger than 3.15. However, this does lead us into a topic that we want to think about. If the interval, if these endpoints, you can see they go from here to here, if they were a little narrower, if the interval endpoints slid in towards the middle, if they got narrower, maybe if they ended up here and here, and actually they don't even have to move there, right? What if they ended up like right here? Just barely moving a little bit. If they got a little bit narrower, that 3.15 value here would pop outside and we'd be able to make a stronger statement. And so that's obviously a topic that we want to investigate. We want to take a look at how can we make a confidence interval narrower. But that's another topic for another time. Right now, what I want you to think about with the video and the lecture that we have here, hopefully you have a general understanding of confidence intervals, have a decent feel that repeated sampling, those intervals sliding back and forth, that is the key to confidence intervals. And when I say it's the key to all confidence intervals. We're looking at a large sample mean, but you're going to see that same key over and over again. So hopefully you got a taste of that, a sense of what a confidence interval is doing. Specifically, in this video, large sample means. Hopefully you'll be able to find z-values. Hopefully you're starting to understand the interpretations. Now the practical, the theoretical, these questions, you're going to see that theme over and over again. Because again, these interpretations are not unique to large sample confidence intervals. We'll see them with small samples. We'll see them when I change from means to proportions. This is the way that we interpret confidence intervals. We state our practical. The reliability statement shows up as a theoretical interpretation. And then I'm going to ask you some questions and expect you to be able to answer intelligently. If the point falls outside the interval, you're going to be able to make a strong statement. If the point falls inside the interval, you're going to say a little dweeby, maybe, I'm not sure, but that's the best you can do. At a 92% confidence level, it might be bigger than 3.5. What if I ask you less then? Is mu less than 3.15? Don't you have basically the same answer? At 92% confidence level, the mean might be less than 3.15. It's the best you can do. So chew on that for a while. Take a look at that, and then when I come back, I'm going to be talking about the interval width. I'll probably do some computer demonstrations for you, and we'll take a look at small samples. Hopefully you're going to find that when we go to small samples, there are going to be some changes. Like for instance, the z-distribution is not going to work with us anymore, but there's going to be a lot of similarities as well. In fact, there's more similarities than there are differences. So hopefully this is the big bulk of the material, and then the rest of the stuff will come a little bit simpler. So if you have any questions, you know how to get hold of me. Otherwise, have a great week. So long.